synthesis and modification of material. And Germano is in the State University of São Paulo. Okay, so let's start with the large. So probably you have been seeing this in the newspaper, news about the James Webb Space Telescope. This is a tool for exploring the space, and they are scanning the space, let's say. And I have chosen, it's a tool in the infrared, so it's an infrared telescope. And I think there's one image here to discuss with you. So this is an image of Neptune in the infrared. So you see, they have here information, position and spectroscopy information at the same time in the infrared. So they have this image, but it's not in the visible. And this is why they can say something like this. This is in the NASA website. They say, we find here high altitude methane ice clouds. So they are not only saying that it's methane, but also that it's not a gas. So how can they say that? Because they have this position information here, but they also choose one. In this case, for example, you see this is a crystal, one of the phases of methane. It's a molecular crystal. So you have this, you have the methane molecule. Information about the molecule itself, the vibrations of the molecule. And I will show you in a minute an example of something that we have measured in this along these lines. But before here, this is the typical spectrum. This is another planet, exoplanet. And you see here they plot the amount of light blocked as a function of the wavelength. Sometimes they plot it against the rain. It's the same thing. And you see here there are peaks that they attribute to, for example, water. So 1, 2, 3, and they come from different vibrations of the molecule. So when you have something like that, this is a very good signature of the molecule there. And sometimes it's more difficult to say what it is. Carbon oxide, they have only one peak here. It's more difficult. Then if it's gas phase, you have also rotations, and if you have a crystalline solid, you have many phases. And how do we study this? How in the lab and make this link with what they observe? So this we did the region. This is ice film, but ice not from water, from satellite. And it's solid, so we have this cryostat, and we put the gas there, it grows this film. It's microscopic deviation here. And the question is here is it's amorphous crystalline, what kind of signature in the infrared should we have here? So we have phonons here, it's solid, but it has this molecular character. And recently this was like the other one, this was observed in the Sant'Anna planet. It's a dwarf planet, beyond Neptune. This is not the solar system. The solar system is this small thing here, and it has this orbit around. And they say, they were not expecting C2H2 there. So they think that it may come from the irradiation by protons coming from the sun, they don't know, on CH4. So here you see, saying something about disorder here is relevant because this process here is highly affected by disorder. So how we do that? We go to the lab and measuring different conditions, this absorbance spectrum for this film, this ice. And what we see is playing with temperature here. We only have two possible signatures. When you change the temperature, it doesn't go slowly from this to this. It's either this one or this other one. So these are two different phases. What can we say about if they are crystalline or amorphous? So one thing that we did also here is use the ion beam, an ion I think, and a proton ion beam to irradiate this. So when we do that, we come from this one here to this one here. So this means that the disorder has increased here. This is amorphous. But this one, we still don't know. To say something about that, we have to compare this with some prediction from the theory. And that's what we do here. So these are necessary functional theory calculations. And you see here that this is also like the one before. This is a solid, but a molecular solid. Then the first thing that we tried was to calculate for this crystalline phase, but it doesn't work. It's too much here to the right. And then we came with this idea. Let's try to simulate the amorphous one. And we are trying here to describe the experimental data with this model using the monomer calculations and the dimer calculations here. You see, this is there are 4 peaks here, they generate. But when you have them side by side, when they come close together, the vibrations are affected by the other one. So if these two were far apart, there will be only one peak here. But when they came close, like in the amorphous solid, they will see each other, and then it breaks the symmetry. And they all have the same vibration mode, but here they are out of phase, here in phase, here in plane, here out of plane. So you have this 4 peaks that will show up as peaks in the experimental. And here you can see that they are about the same width here, the height is similar, and then we proposed this. We can describe both peaks, this is the other one, as a combination of the spectra from calculated for monomers and dimers. So what we think that is happening here is ice that we are producing in the lab, maybe similar in space, is that we have 2 amorphous phases. This is the bottom line of this part of the work. Something very similar happens with water. This is well known. The phase diagram of water is very complicated. You have there also these 2 phases. They are amorphous. This is high density and this low density. We don't know if this corresponds to the same kind of change here, but this is what we are proposing. We need more work when you go to space, this will change the interpretation of things. See that? Okay, so let's go to the direction of the small now. If you want to do the same kind of thing with small objects, really small objects, but first, what was our motivation in Rio to do this? To look at spectroscopy on the nanometric structures. So this is the kind of thing that we were studying just before the pandemic. We used ion beams to modify thin films, different kinds of thin film. These are two examples. Here we have this is a substrate, and here you have this thin film of gold and a small denser layer, 5 nanometer here. And when we do that, this will not just go down with the same height everywhere. Structures will show up here that we want to study. Same, this is a metal, this is a quite different material, this is silicon dioxide, amorphous film, but the same thing here. When you irradiate with high intensity, structures will show up here. And for example, here you can see, when you irradiate, you will eject both silicon and oxygen atoms, but not in the same amount. So there's sputtering, we say, but it's in principle, there are preferential sputtering rates for each one of the atoms. This will break this balance, and soon it will not be SeO2, but SeO(X), something. And by doing that, what kind of molecule is formed here? How does this signature change? So we need information on the binding of the atoms to each other. And the infrared is good for this, we saw before, but you will see that there are also problems on this. This is the machine that we have there. I will not go into details, but if one wants, there is this instrumentation paper about how we use it specifically to study this thin films. This is also before we started to work with the infrared to characterize the sample. Here's where we saw that we needed something like that. So, as I told you, when you irradiate this, and this is titanium. Connected with interferometry. This is just the scholar for really, if it's reasonable to think of that, because I saw it here. It was with our eyes here, we are doing this kind of spectroscopy here. But there are some weird stuff also that this happened here. You see, this looks like here to the eye, looks like a hole, but it's not really. They are this small structures here. There is some plasmonic effect here that here it looks like a hole, but it's not really. So when you push to the limit of this spectroscopic imaging techniques, things start to go wrong. So this is an example. Look the dimensions here, 400 microns, 40. Here we go to really small to the background here. So the silicon here, this we can show with atomic force microscopy, is not uniform. There are patterns formed here, and we don't know with atomic force microscopy what atoms are these, what elements are these. We know silicon is there, but what else?
But we can model this and, okay, this is experimental data. This is small square here theory. That's kind of theory that more or less with modifications that Turing proposed to explain these patterns in animals, for example. But there is also the sputtering. The equations are a little bit different. They are similar. And in this, they suppose there is preferential sputtering here, and the current hypothesis is that silicides are important. I don't have any information about if they are present here and how the silicon and titanium atoms are binding here. So we need to say something more. We need the kind of information that the infrared spectroscopy gives. Okay, this is another example. This is also a film, but the other one was metallic. This is insulator. But something weird happened also here. Changing the fluence, the fluence is changing here in this direction. If it's low, there is nothing really going on. But above a certain critical fluence, there is a really dense forest here of structures, of nanostructures that show here. So this is another motivation to check what's the difference between this region, between what's happening, what's the structure here made for, and the background, for example. For that, we'll go later to the infrared spectroscopy also. Oh, this is the same question again. Let's go small. But before, I think this is a good illustration also. Much before going to the nanoscopic, there are limits appearing here by the diffraction limit. This is from a photographer in the internet, and he shows that you have tricks, he suggested here, to improve a little bit the infrared imaging. But anyway, they will be limited by the diffraction limit here. Let me show you this other one. What's the problem? So the naive idea to use the infrared to study these nanostructures would be to have a very collimated beam of nanometric beam of infrared light and scan the surface. It doesn't work because of the diffraction limit. You can see some examples here. If you have two apertures and there is infrared light emerging from them, the details may vary with the size of the aperture and with the wavelength. But eventually you have these two different structures will show up as one blurred structure. This is a physical limit here. So how can we beat this limit and use some sort of microscopy in the infrared? So this is what people imagined and created. And the technique is, there are some tricks here. I will not go into detail, just point a few ingredients here that are important. So the idea is to start with atomic force microscope. Here's the tip. But then what they do is that they cover this with metal. They put the sample close to the tip. The tip is oscillating. And then they use a beam of infrared light and illuminate this region. Then they look at the scattered light. And they look at the signal, in coincidence, I say, with that frequency, only in that frequency. So doing that, they can measure what they call the near field component. So even though you are looking from 1 meter away, I don't know, you are looking at this because this is the part of the spectrum that you get because you are locking in this frequency. The interpretation becomes a little bit more complicated than before because here you have the tip and the sample. And the sample, I like this image from these guys because they show that the sample is modified by the by the tip. And what you measure actually is the set of both together. And then you have to analyze this. But your signal will have information about the surface. Another point is that it selects the surface. So the polariton will be here. You have a quasi-particle. I'll show more about it in the next slide. But it will be created here, a quasi-particle that is limited to the surface here. So we are both limited to a region around the tip in the plane and in the vertical also. So it really looks for nanostructures there. A little bit more about this particle. So to use the technique, you don't really need to know the details, but just to get an idea, this is not a phonon anymore. It's not a photon also. It's a combination of both. It's a light matter excitation, so a different quasi-particle. And this is the dispersion relation. The details are not important, but there is, you see here, this is just for the photon. This is for the phonon, and you have the combination of both here. Then there is also a forbidden region here that is forbidden unless the negative part of the electric function is negative. Then your propagating wave will become this evanescent wave. And this is what we measure. So this is the important part. If you want to measure something with this technique, check first if there is a region in the electric function that has this negative part, negative value for the real part here. Otherwise, there will be a phonon, but not a polariton. So this is the important thing in this slide. This is a work all dedicated to this. If one wants more detail, how we beat the diffraction limit with this technique. And here, I will show you two examples of what we did there. So there, where is there? It's at the Brazilian light source. So they have a beamline there for this. So we prepared the sample at Federal University, irradiating this film, the sample with fluorine ions with 20 keV, I think, in this case. And then we went to the synchrotron light source to study. Use it. Since here it's acronym for the synchrotron infrared nanospectroscopy. And there is a beamline there for this. There are a few around the world. In Berkeley, there is one also. They were pioneers in this technique there. So we prepared it and went there. Here's the tip illuminating. And this is one of our results. I will show some details. But you see here, they are quite different, the spectrum, with before the irradiation and after the irradiation. So we are increasing the disorder and the amount of defects in the sample, and it's killing basically the surface phonon polariton. So this is a way to point, because there are other things that may end up showing up in the spectrum, but they are not really the phonon. So this is the first thing. The other thing, keep an eye on this small peak here. It was not known before that it was there. Let's see what it is. Okay. So this is good also to understand a little bit more what I am calling disorder and defects here. This is the dielectric function as a function of the wave number proportional to the energy. And three different curves here. This is for crystalline quartz, alpha quartz, crystalline silicon dioxide. This is amorphous from these people that measured. They are all experimental here. And this is for what they call SSO. But I mean, this is really as this thing here with less oxygens. So the first one has this crystalline structure. Each silicon atom is connected to 4 oxygen atoms. The same thing happens here, but it's not crystalline. I mean, this is what I'm calling disorder. So it's basically the same thing, but there are variations in the angles and in the distances. So this thing here is this one disorder. Our film in our study starts like this. And then when we irradiate, it was already disordered before. So in this case, we are adding defects here. We are removing with that preferential sputtering more oxygen atoms than silicon atoms. So this is what I came to represent this. But really, they are not. They can be sputtered or they can be defects here, interstitial defects. But this one is the first one. The second is the first with disorder. The third is the second with more defects. And then you can see here, the important stuff is this. We have to look for this region with a negative part in the electric function. So for the crystalline one, it's very clear. And there is also this thing showing up here for that second peak. It will give origin to the second peak, not at the same position, but then in the disordered one, you have the polariton here. But it's not clear if there is something here. We found it. And if the amount of defects is very large, then you should expect that no polariton will be present. Then here are our measurements again. We have the absolute value and also the phase. So these are the real and imaginary parts, but we can look at this one here. So it's basically the same that I shown before with different colors. You have here before the radiation and after the radiation. And then modeling this with theory, what's the theory here? We call it finite dipole model, it's standard. We model the tip here by an ellipsoid, and then the scattering of light by it. And also the medium here, you need here as an entrance for the theory, as an input, you need the epsilon. And then what we did here is to combine, we use an effective medium theory to combine the epsilon from silicon oxide and SiO. And then with different percentages here. And we see that the general trend is what we observe here when we irradiate the material. So that's what we think we are doing here, creating these defects and healing the polariton. This one is just have the pristine sample, the non-irradiated one, experimental in blue, and here the theory with the best fraction that we could find here of the SiO. 20% at the beginning, and then after the irradiation, 60%. So that's what we are saying about the sample before and after. So there was a little bit, there was some defects before already. That's what we found. But after the irradiation, it's higher here. You see here the theory is not enough to explain this small peak here. So we did something different here. This may be helpful also to understand the idea of having different modes in the vibration modes in the solid. These are from DFT calculations again, but for crystalline, we could not do this for the amorphous one. It would be too complicated, at least for us. So we did this with quartz, the crystalline one. And these vibrations, they have characteristic frequencies here. This one is here, this one is here, and this one is here. This is a symmetric stretching mode, and these are anti-symmetric. So if there are two here, why one is so large and the other one is so small? It's something similar to the dimer that I had shown before. What you really need to do here is to look at the vibration, look at the neighbor. How is it vibrating? So in this case, so there are two units, let's say like this, one on top of the other one. And here, the details are not important, but you see that they are in phase. So you give rise to this one. This is also anti-symmetric stretching, but here they are out of phase. So the dipole momentum will be small, and you see only this thing here, but it's there. It's there also. So this is the points that we captured here in this work. Okay. Let's see. Okay.
Will this give rise to different surface lengths?
Yes. In that diagram, the constant line, you have the photon like this, and the constant has origin in a phonon. So these are three different phonons with three different energies. You see here, 1, 1, 2, 4, 1, 2, 3, 3. Different lines. You observe them there. In the book, they have been observed before. People know that they are there. So, but only here at that Surface Phonon Polaritons that people never saw that before. Yeah, also because this is not the crystalline one; it's the amorphous. So it depends a little bit on the details on the sample. It's disordered. So you may look at one piece of the sample and see it clearly, and not in the other one. There's also this. Okay, so now the second film. This is the silicon dioxide one. I have shown this before. So after studying this and looking at with the microscope tip here, and we came to the conclusion that what's happening here is the following. You start with SiO2, but then with the radiation, you have the preferential sputtering. You get rid of oxygen more than silicon, and then you start to go far from the thermodynamic equilibrium and create this in your sample. So this X starts as 2, and then as 1.5, 1, and even lower. So if you get far enough, and you do it if you have enough ions instant, this reaction will happen. This is what people call a disproportionation reaction. It's also been found in with other factors, not ion beams, but other factors introduced in these defects here. And then this thing is transformed in these two. This is pure silicon. Then you started with this thing, and you have now nanostructures of silicon, pure silicon, with defects, but silicon. And you go back here to 2. So, and then what we see here is this kind of stuff, but full of defects. So I'll show you. So this was our strategy again. We prepared the sample there at the accelerator. In the sample here, we have regions that were irradiated with different fluences, different amounts of ions per area. This is just at this moment, it's just atomic force microscopy, no information about if it's the binding, the chemistry, let's say. And then we, at the Brazilian light source, used the technique that I have just described to study the sample as a function of position and spectroscopically. This is a zoom, let's say, in one of the structures. It's not a very different scale here. And then what we can do now that we couldn't before without this technique is to go with the microscope tip here and measure a spectrum, and then here and measure another one. So in some sense is what they are doing with the James Webb. One point spectrum, another point spectrum, but now in nanometric dimensions. And what we see is that at the background, we have signs of this SiO2, but there is this thing that is now appearing also that we will discuss in the next slide. There is this new stuff, but there is some signature of silicon dioxide here. Here, it's basically flat. And this flat behavior is what we expect for silicon. And the amount here is also consistent with silicon. So we are seeing here that disproportionation reaction. Huh? We have these two things that have shown up here. Finally, we got a reason to use this technique. And then let's go ahead to understand what is this structure here. It was not there before the irradiation, and then soon it appears after some time. This intensity is really high of the ion beam. This is a high dose, a high fluence irradiation, the numbers here. And then we start to etch the surface. Starts with 50 nanometers, then 49, 32, and at some point it will be off. But since the beginning, it starts to show up here. You see here again that the peak, it's still there, the signature there of the silicon dioxide. And then, but what is it? No? They are here at the experimental spectra. They radiated once, not before. And the we first thought that it was just a SiO, but it's not in the right position. And we have sharp features here that they are not expected for this situation here. So what we did is that we went there back to the modeling and used the electric functions for defects in silicon. And use the same model to see where the signatures of those would appear here. So what we found, this is our experimental data here. This line. This is from another group. You see another interesting thing. This other group, they didn't use a synchrotron. They used a laser. You can do this with a laser. But the thing is that the range that is accessible here for a laser is small. And with the synchrotron, that's why they started here and stopped here, because of laser limitation. While with the synchrotron, actually, we could go much lower than this with the proper detection system. And we could go here easily to 3,000. And so we have a really broad. This is why it's more interesting to use this with the synchrotron radiation. Okay, but then going back here, this part is basically the silicon dioxide. But here you see, the details are not exactly the same, but we can have sharp structures here corresponding to, for example, this defect is this is silicon with this defect. Vacancy together with an oxygen atom in different configurations, two oxygen atoms combined. This is so chemistry again, combined with a vacancy. And many different combinations here, but all of them vacancies and oxygen amounts here, 1 or 2 or 3 atoms combined. So that each one of these defects will show up in a different position here. And combined, they will give you a peak in this region here. Okay. What else? Let's see. Here, my motivation at the beginning, it was related to this titanium silicide, for example. Where is it here? So it's not here in this range. So things are not done yet. Because the mass is higher than the oxygen. So it would appear somewhere like here. I told you that the synchrotron is good for this, but you need the light, the infrared in the range, but you will need also the detectors in that region. So right now, they don't have it at the Brazilian synchrotron light source, but they will. So I will show you here how things are going there. And also, I'll take this moment to show you that there are many opportunities for you to work there. It's a national lab. It's really open with a very nice procedure to apply your proposals with a fair trial. And also there will be there may be some kind of scholarship for people going there also. But before, this is the list of the beamlines there. It's a really beautiful machine. It's a top, something it started operating 2 years ago, I don't know. So many of the beamlines are still being mounted and designed, and so it's partially operating, but it's you have to go there. It's a really, really nice one and open. So this is one that I have used, this infrared micro and nanospectroscopy. They call it imbuya. These are names of fruits and the trees and birds. And you see here, it's starting, they say it's starting 550. This is proportional to energy here. It's a unit normally used. But it's not true because the detector there, they are starting right now at 750, something like that. But they are building this other one here. It's being assembled. I saw the beginning of the work there. Probably it will be available, this one, in 1 year or 2, I don't know. And this will go to the terahertz. It will go much lower here. Converting, you see, they have the different energies because this is more typical of terahertz work. But converting here, they will be around here. For example, the titanium silicide will be here. Many vibrations with heavier elements. Many stuff that we would like to do there. We cannot do here right at this moment, but it will be available soon. And the same thing happens for all these beamlines. So the ones that are working, great. But it's good if you, maybe it would be a nice idea to check this and see if it fits your needs now and for the future. And this one here is specifically here. They have financial support, partially. It will be more expensive than this. But anyway, also for people from here, from foreign institutions, from Latin America and Caribbean, for example, they will support two users proposal here with, they will pay you, put part of the air ticket, and they have this lodge inside the lab. You can stay there. Very nice also. And lunch, free lunch for 2 people. But 2 is not enough for an experiment there. You need a larger group, let's say. But that's an idea for you. Okay, I think this is it. So thank you very much.
Thank you, Professor. So I wanted to ask regarding the source choice. You mentioned that using a synchrotron source expand the accessible frequency range over infrared lasers. That's pretty clear, much broader band. But my question is in regards, could you elaborate on the practical trade-offs? I mean, specifically, what crucial frequency ranges, or material phenomena like low energy modes become accessible with synchrotron, and what challenges such as signal to noise radio or beam stability does this source introduce compared to a high power tunable laser?
Well, when you can use a laser, the laser is much better. So if you have the same frequency range, the intensity will be much higher. We will be able to work with higher modes here. It's better. If you only need that region, laser is better. So you only need to go, and there are actually microscopes that people sell, combining 2 lasers that expand the region a little bit because they are 2, and they are fine. So it's okay. So the thing really here, I'm not a beamline scientist here. I don't know every detail, but I can tell you that the region, the nice region here, covers this oxygen, vibrations, carbon, things related to hydrogen. So they will be here up to 3,000 maybe. The people from polymer studies, they use this a lot. So you have nice works on this region, they go there often. If you go higher, actually, I don't know if they could, nominally, I think that beamline, they say they go up to 6,000 here. But the detectors that they have there, that's another thing. You cannot use only one detector. You need to use, then you need to ask them to change, and it will take some time. If you have him there for 4 or 5 days, I don't know, that may not be the case. But that's possible to change it to expand this thing here. So regarding lasers, this region here, so we got the vibrations of hydrogen, carbon, oxygen, they will be around here. And then the heavier stuff will be here. So right now, we cannot do it. So anything heavier than oxygen vibrating here, we'll not see it. But with the new beamline, yes. The other thing that we can do here also, I only talked about the polaritons, huh? But you have plasmons also. So if your sample has the right density of electrons, they will show up here also, the plasmons. So this is another kind of study, but they will not be sharp peaks. They will be really broad peaks. So this is another reason to go to the synchrotron, because this kind of broad peak of the plasmas in this region, you cannot do it with laser because it's intrinsically large.
I have a question. The ion beams are normally very, very small. How do you irradiate the large sample? The large you showed at the beginning, the one with 1 centimeter. And how long?
Okay, that one actually was we did it in the Catholic University. We just used defocused the beam, and the intensity was not really strong then, but it was okay. I didn't.
And how clean does the sample has to be?
It depends. I mean, if it's dirty, but it's in another region, you are not really concerned with that. Now, if you have a contamination in the same region, yes, you do. But regarding the beam, the size of the beam,
you defocus.
What am I doing here? Okay, let's go there. In some, we use it, as I told you, in different modes, the accelerator. Then, in part of the experiments, this, well, let's try this. Connect again. Bad contact. Okay, it's back there. Okay, in this experiment, for example, we used the broad beam. So we irradiated the whole sample. This was maybe 4 millimeters, and we made it like 8, 10, I don't know. But it was an experiment for low fluence. But in the other slides, I think I have shown. Oh, this one. You see, it's not uniform. In this case, we needed really high currents. So what we did actually, that's explained in detail in that instrumentation paper, we put the sample inside the ion source, in this case. And then the current is really high. This is why it's cesium, because we only have the cesium ions inside the ion source. And there is a shape here. So how we use that? The fluence is not uniform. This is good in this case because the radiation, the fluence was really high here, and it goes down in this direction. And this is what we are seeing here. So we later come with a microscope and probe the sample in different positions. So when you do that, we are probing as a function of the fluence.
Okay. And this is a sputtering ion source.
This is a SNICS ion source, the sputtering ion source, working with cesium.
My last question. One of the big deals in synchrotron technology is to remove the higher order harmonics from the ion beam.
Mhm.
And I saw that there is an ion beam and a beamline with micro EVs. I saw.
Uh-huh.
How do you handle the second order harmonics?
Well, yeah, I will tell you this. I don't know the technical answer for this, but this machine is completely different from what we saw before. For example, just to give you an example, we use it to have this electron injected in bunches, and then it was decaying with time, then injected again. This is top mode. It works with constant amount of electrons there. So why is it so good? The intensity is higher, but also it doesn't hit with different amounts of energy as a function of time, the optical elements. So before we had, at the beginning, the beam was here, then it was shifting. This is gone. Gone. So we have really high intensity, really stable ion beam. And I cannot say because I didn't ask it there, but I'm pretty sure that it's not a problem. Second order harmonics there. They did a really, really good job there.
Well, if there's no more questions, let's thank again Dr. Sant'Anna.
My pleasure. Okay.